Okay, folks, so now we're going to talk a little bit about games where we have richer action spaces, so people can take some level of action, but beyond 0, 1. And I want to talk about just two examples of this that give some illustration of these things. And one is going to be basically a game of substitutes that's going to have a lot of relationship to the Best Shot Public Goods game that we looked at before. And another game is going to be one where there's games of complements, and that'll be a different one, and it'll tie back to network structure more easily. So let's have a look at these things and try and understand a little bit about them. So the first one is a game on networks, also known as a graphical game, where we're choosing now levels of actions. We could have it in 0, 1. We could have the action, it could be xi in 0 to infinity. So some people are taking some level of action. And this we'll look at as in work by Jan Bramule and Rachel Cranton. And the game that they're thinking about is one where people are choosing some level of information to acquire about something. Okay, so you're expending some effort, and this effort is learning about something, and how much time do I spend learning about this? So it might be learning about, in California, we vote on things in terms of propositions. How much time do I spend learning about this? And then maybe my friends can just ask me and free ride on the fact that I do the research, or maybe I free ride on them, and so forth. Okay? So the structure that they look at is a classical public goods structure. So the payoff for any given individual is going to look as follows. So what are you getting? You're getting some function of your own action, xi, plus the action of your neighbors. So you've got sum of j in your neighborhood and what those j people are doing. Okay, so that's the benefit you get. You get some benefit from the overall level of public goods that's being done. And generally, this is going to be a concave function. So initially, there's high benefits to this, but it is going to tail off with the level. So as we think about the total level that's being provided, the total level of the sum of x's, as it goes up, we're going to think of this as being a concave function. So eventually, more and more learning, it's just not worth any more information. So information, a little bit of information is really valuable. A little more is a little more valuable. Eventually, it's overload. It's not worth anything to me. Okay, so we've got a concave f, and then each person pays a per unit cost of their effort. Okay, and then we pool our information, so I get to learn my information plus everything that my neighbors learned. And we pool that together, that's the value I get, and then I get a nice concave function of that, and then I pay some cost per unit of effort that I have. So that's a very simple structure. And once we have that kind of structure, we can so let's assume that this thing's nicely differentiable. We can take a derivative of it. We can also look at the maximizer of this. So suppose that I just look at the function where I look at the total effort that's provided and look at the total cost. Okay. And I want to look at a situation where I maximize this thing with respect to x. So maximizing, let's suppose that I want to choose the x which maximizes f of x minus c of x. Well, maximizing that, I'm going to set f prime of x minus c is equal to 0, or f prime is equal to c. So let's let x star be the solution, that if a given individual was choosing how much total effort should be provided, they had to pay the cost for that whole effort, they would choose x star. Okay, so we'll call x star this level. Okay, so what's true about x star? If you look at any pure strategy Nash equilibrium, now let's suppose that each person chooses the x's and they look at what their neighbors are doing. In all pure strategy Nash equilibria, the total amount that any individual is getting in their neighborhood has to be at least x star. Okay? And why is that true? Suppose that the amount that was being provided in somebody's neighborhood was less than x star, right? So say x star over 2. Well, if given that this is a concave function, x star is the point at which this derivative is exactly equal to c. So when we look at where f prime is, that's equal to c. The slope is exactly equal to the cost. So if you were seeing less action, then you would have f prime be greater than c. And so that means a little bit more action by one person. So if I add a little bit extra x, the gain I'm going to get in terms of my f is going to have a more rapid gain than what I'm going to lose in terms of cost. So if anybody is seeing less than x star in their neighborhood, they would like to increase xi. So if this sum, if that was less than x star, then you should increase xi. And so that could not be a Nash equilibrium. I'd strictly want to increase my activity because I want to push us up to this level where the trade-off begins to be just equal to the cost. Okay. So what that tells us is that in a Nash equilibrium, if it has to be that everybody's getting at least x star, and if I'm getting more than x star, it could be that there's lots of people that happen to be providing public goods for me. So my neighborhood is really full of people providing lots of public goods. If we're in a setting where I've got extra activity going on in my neighborhood, then it should be that I'm not providing any action. And why is that? Because if we've gone too far, then by decreasing my action, if I'm providing positive action, what I get in terms of the decrease, so again, this f prime is in a situation where by decreasing what I'm doing, I'm actually, so if we're in a situation where I've gone too far, so this is the x star where things are exactly equal, if we've gone too far, then what I would lose by decreasing my action would be less in terms of the slope than the c. So there we'd be in a situation where f prime is less than c. So actually decreasing my action would save me cost, and the loss and benefits would be less than that. So it has to be that if we're over, then I'm providing nothing. Okay? And that is possible in some of these situations, that if I have lots of friends providing public good, I'm getting too much, I free ride completely. Okay? So that's a basic structure. And so what that means is that then equilibria are going to boil into situations where we can talk about two different kinds. One is where we're in a situation where there's things are distributed where everybody is providing some action, and the total actions are just balancing exactly up to these x stars. Everybody's seeing exactly x star in their behavior in their neighborhoods, and everybody's acting enough to just balance these things. And then there's specialized equilibria where some people take actions and others don't, and where basically the people who take actions are just going to specialize and produce the public good, just like in a best shot public goods game, and then those people around them are going to free ride completely. Okay? And so to get a feeling for this, let's have a look. So let's suppose that we'll just normalize x star to be 1. Let's look at, here's a few different equilibria on different networks. Here's a situation where we've got a specialized equilibrium. These people provide the full action. Their neighbors free ride. Everybody gets exactly x star in their neighborhood. Nobody wants to increase their action. In fact, some people, these individuals, get more than x star. They get 2 times. So they're happy. They're getting double the provision of public goods. They certainly don't want to contribute anything. Okay? And these people are getting exactly 1. They're providing it because their neighbors are not providing anything. Here's another equilibrium. Everybody provides 1/3. And that balances because we're in a situation where each person is seeing exactly x star in their neighborhood. So nobody wants to increase or decrease, right? So this is a distributed one where we've got an exact distribution. Okay? And this one is similar to the first one, but just with roles reversed. Okay? So you could generally, if we had disconnected individuals, they'd each have to provide 1. There's nobody else to free ride on. You could have situations like this where the isolated person, their friends provide, they don't have any friends, so they provide the public good. Here you could have either person provide it. You could also have an equilibrium like this where they do a half, right? Or it could do one where you've got 3/4 and 1/4. So you could have a whole series of different equilibria, and then in each of those cases, the other person would be providing one. You could have situations here that look like the best shot public goods. You could have ones with these distributions. So there's a whole series of different equilibria. Some of them are specialized, where certain people end up doing 1, other people end up doing 0, and then there's other ones where distributed, where you've got some actions by different players, but they're adding up to 1. Okay. Okay. So we can begin to see the connection between this and the best shot public goods game that we saw before. If you look at the specialized equilibria here, those are going to look like maximal independent sets, right? So you have some people just provide the full public goods, their neighbor's free ride, and no two nodes that are connected can both be providing the public goods. So you end up with every node in N is either in this set of S that provides the public goods or linked to somebody. And proposition by Bromley and Cranton then is a set of specialized Nash equilibria here are profiles such that the maximal independent set is maximal independent set is exactly equal to the set of specialists, people providing the public good. Okay, so that's just a straightforward extension of what we saw before in the public goods game, the best shot public goods. But now we're actually allowing people to take multiple actions, and we see that the specialized equilibria correspond to that. Okay. So what's interesting in terms of the Bromley and Cranton analysis is they show that the specialized equilibria are actually ones that have a nice property, and it's a sort of a stability property. So imagine what you do is you start with some set of strategies that people are playing. So let's look at our equilibria and ask which ones are sort of stable to perturbations. And what we'll do is that we're going to perturb this by changing everybody's actions by a little epsilon. And the epsilon could be positive or negative. So we could, move some people, we bounce some people up so they provide a little more information, other people down so they provide a little less information. So we start at some point which might be an equilibrium. We want to ask, is that stable? We perturb it a little bit. And then what we do is we look at, okay, what's the best response? So if everybody was choosing their maximal action, given what everyone else is doing under this perturbation, what do we get? Okay, so we go from x0 to x1, and then x1 goes to x2 and so forth. And what we would like is that if you perturb things by some small epsilons, if you always converge back to x, then we'll say that the equilibrium is stable. Okay, so that's the notion of stability. Let's first think of a dyad. So we've got two individuals, these two individuals. And let's suppose that person 1 is doing something, say, like a third, and person 2 doing 2/3. That's not going to be stable in the sense that if we perturb this a little bit, so suppose we move this down to 1/3 minus epsilon, and this up to 2/3 plus epsilon. Well, that in fact is also an equilibrium. So if we did that perturbation, it wouldn't go back to the original one. It would actually stay at this one. Okay. So in a dyad, no matter what numbers you put in there, we could put in 0 and 1 and have this go to 0 plus epsilon, 1 minus epsilon. So no matter what numbers you put in, as you perturb this, it would stay there. So as long as x1 is less than or equal to x2, add a little bit to x1 and subtract a little bit from x2, you would stay there. So you're in a situation where you end up not having any movement in terms of the perturbation, nothing stable. Okay. But when we look more generally, the equilibria the only stable equilibria are necessarily going to be specialist equilibria, and they're going to be such that every non-specialist has exactly at least two specialists in his or her neighborhood. So for instance, if we look at 3 nodes, and again our x star is 1, this thing is stable. These three are not stable. Okay, and let's just go through and try and understand why is this stable. What's the logic here? So let's suppose that we perturb this a little bit. So for instance, we take a little bit of an epsilon away, so we take this person down to 1 minus epsilon, and we bump this person up to epsilon. And let's just keep this person constant for now. If we do that, and now we look at the best responses to this, well, this person has already a neighbor providing at least one. They're still at 2 minus epsilon in their neighborhood. They're way bigger than the x star of 1. They're getting too much action. They can get rid of their epsilon and go back to 0. So they're going to tend to go right back to 0. Once they go back to 0, this person's going to go back to 1, and we end up going back to the situation that we have. So here the fact that I'm already getting too much means even if you perturb that, I'm going to want to go right back to 0. So the people that are in the neighborhood of these specialists are going to stay there. If they have at least 2 specialists in their neighborhood, they're going to go back to zeros, and that means the specialists are going to be forced back to 1 because all their neighbors are providing zeros. Whereas this one is unstable, and it's unstable for the same reason the dyad was, right? We could make this a 1 minus epsilon, and then move this guy to epsilon, this guy to epsilon. Once that happens, well, then these people are happy, but this person's going to want to decrease more, and it would actually move eventually towards this equilibrium. We could change this by moving this to minus epsilon, add an epsilon over here. That would still be in equilibrium and so forth. So the only ones that turn out to be stable turn out to be the ones that every specialist has specialized equilibria, and such that every non-specialist has at least 2 specialists in their neighborhood. Okay, so you can go through a sketch of the proof of this. Basically, the stability of such equilibria for perturbations of this for the non-specialists, the best response, they go right back to 0, and you converge right back. For any other equilibrium, there is somebody providing goods that's a non-specialist, and then you perturb that agent up and the other neighbors down, just the way we did, and basically you can work through that kind of logic. So the idea of the proof is much similar to what we just worked through in terms of the examples, and you can deduce this proposition in that manner. Okay, so what that says is that these specialized equilibria are somehow special in this model. So you get they're stable in the sense that if you do perturbations, then you're going to get pushing people towards that. Let me just sort of make one comment on this, and it's sort of an interesting contrast. Another way we could think about, so here we've got a game with multiple equilibria. There's lots of different equilibria in this game. And, part of the reason that one's interested in applying these stability concepts is to find out, are some of these more natural equilibria than others? And so if we perturb them and we get back to them, we say, well, that seems to be a more natural one than another one. Another way we could think about stability is instead to think about pairwise stability, right? So suppose your links are costly. And if I'm specializing, and I've got a bunch of friends who aren't specializing, I'm providing all the good, they're not doing anything, I would start dropping links to the non-specialists, right? So in some sense, in that world, what you would have is the only reason people would be willing to maintain links would be if their friends are also providing some of the local public goods. So I only want to keep these friendships if they're actually providing some value. And so there, what you're going to get is the non-specialized equilibria are going to be the only stable ones. So what this says is that, it depends very much on what kind of stability notion you put in as to what you might select out. And whether you think about perturbing the network or perturbing the actions, you could get very different kinds of conclusions. And so, ultimately, I think what this says is there's still a lot we need to understand about these kinds of games. They are tractable games. They have some interesting features. Some of them tie back to some of the things like the best shot public goods games and so forth, and they can be interesting to analyze further. Okay, so that's one example of these kinds of games. If we begin to introduce heterogeneity to these kinds of things, that's going to change the nature of equilibria. We could begin to enrich things that way. There's a lot of enrichments we can make in this kind of games. And what we're going to do next is look at another class of games. And this other class of games is going to be one where we allow for strategic complements. And there, the games, again, are going to be nicely behaved in the sense that it'll be much easier to get a full characterization of what the equilibria look like, and it'll be nice. We'll have some nice relationships to the network structure, and that'll allow us then to